Welcome to this explainer. Today, we're going to do something really cool. We are going to forge a universal mathematical key. We're going to unlock how entirely different physical realities, things you can actually touch and measure in completely different ways, are governed by the exact same mathematical DNA. It turns out a whole lot of mechanical and electrical processes can be represented by the very same simple mathematical structure. And by the end of this, you'll see exactly how.
So think about this for a second. What do a moving physical mass and an electrical circuit possibly have in common? I mean, on the surface, absolutely nothing, right? One is all about friction and heavy weights, and the other is dealing with invisible volts and currents. But to answer this question, we actually need to strip away the physical world for just a minute and look purely at the underlying structure.
Okay, let's dive into the foundational equation of a first-order system. It's called first order simply because it only involves the first derivative of our output. Basically, in this universe, you have an input that drives an output. But their relationship? Well, that's governed by two extremely important parameters.
To truly understand how this system ticks, we need to define those two parameters. First, we have tau, which is our time constant. And then we have k, which represents the static gain. The time constant tau is all about speed. It determines how rapidly the system responds to any changes. A smaller tau means a much faster reaction. The static gain, k, on the other hand, dictates the steady-state relationship between the input and the output. It's essentially telling you how much output you're eventually going to get for a given steady input.
Now, if we hit this system with a Laplace transform, we can shift the whole thing from the time domain over into the frequency domain, which gives us our transfer function. And this beautiful simplification reveals something absolutely crucial. The system has a single pole, and it's located exactly at -1 over tau.
So what does this pole actually do? It dictates stability. If tau is a positive number, then our pole is negative, meaning it sits safely over in the left half of the complex plane. And that guarantees what we call BIBO stability, bounded input, bounded output. In plain English, it means if you feed the system a bounded, limited input, it is guaranteed to safely produce a bounded output. It's not going to just spiral out of control on it.
All right, armed with this theoretical foundation, let's take our universal mathematical key and actually unlock our first physical door. We are going to set up the forces for a mechanical mass damper system. To do this, we'll define our velocity, identify our forces, and apply good old Newton's second law.
Picture a mass being pushed forward, driven by some applied force. But it's not just sliding freely, it's fighting against a damper. That damping force creates a friction that acts in the exact opposite direction of the movement. So, according to Newton's second law, the mass's acceleration is essentially just a tug-of-war between our applied forward force and this resisting damping force.
And here is where the magic happens. When we plug that damping force into Newton's equation and do just a little bit of algebraic rearranging, boom, the math aligns perfectly with our standard first-order model. The applied force acts as our input, the velocity becomes our output, our time constant tau is simply the mass over gamma, and our static gain ends up being 1 over gamma.
I love this because it brilliantly illustrates how physical reality reflects the math. A heavier mass increases tau, which slows the system's reaction down. Just think about trying to push a heavy truck versus a shopping cart. Conversely, a stronger damper actually reduces tau. That means more friction forces the system to reach its top steady speed much faster. This is literally exactly how your car's shock absorbers are designed to smooth out a bumpy road. Okay, let's completely switch gears and cross over into an entirely different physical realm. We are leaving mechanics in the dust and entering electronics. We're going to do this by identifying our voltages, defining our capacitor current, and applying Kirchhoff's voltage law to an electrical circuit. Think about a standard series RC circuit. The exact same current flows through both the resistor and the capacitor. By Kirchhoff's voltage law, the total voltage we push into the system has to equal the voltage dropped across the resistor plus the output voltage across the capacitor. Before we look at the final math, just notice the conceptual bridge being built here. A minute ago, we had a mechanical system with physical force going in and velocity coming out. Now, we have an electrical system with a total voltage going in and a capacitor voltage coming out. We're talking about two totally different universes here, but wait until you see the math.
By substituting the capacitor's current equation right into our voltage loop, we can rearrange the terms, and once again, we perfectly reconstruct our standard first-order form. But in this electrical reality, our time constant tau simply becomes resistance times capacitance, and our static gain K is a perfect 1.
Believe it or not, this exact relationship is the fundamental basis for the audio filters that cleanly cut out high-frequency noise in your favorite pair of headphones.
Comparing these two realities side by side is just the ultimate realization. It proves that these two radically different physical systems, one built of heavy metal and physical friction, the other of copper wires and electrical charge, share the exact same mathematical behavior, the exact same stability conditions, and the exact same DNA. You can literally understand an electrical circuit's response time just by imagining a physical mass sliding against friction. How cool is that?
So we've got the first-order system totally locked down, but I want to leave you with this question to ponder. What happens to the math when we add a spring to our mechanical mass, or, say, an inductor to our circuit? What happens when a system can store energy not just in one way, but in two? Well, we're going to tackle exactly that in our next explainer on second-order systems. See you then!